Today we are going to start with the new topic, that is logic gates. Now what you have learned in the previous session was Boolean algebra, and there we learned different laws, postulates, theorems. The reason we learned over there is because we can reduce the expression, the size of the expression. So because we can reduce the size of the expression, we can reduce the size of the circuits. So in today's session, we will be talking about logic gates. So first is, what is the definition of a logic gate? What logic gate means? It means it's a electronic circuits which has one or more than one input signals to give the corresponding single output signal. That is what the logic gates means. Now, logic gates can be divided into two parts. One is basic and the other one is derived. So which gates comes under basic gates? One is AND, OR and NOT gate. These are the three gates which comes under basic gates. Which are the derived gates? The derived gates are NAND, NOR, XOR and XNOR gate. So you can see here you have basic gates AND, OR, NOT. You have derived gates NAND, NOR, XOR, XNOR. So what we'll be doing is we'll be looking into each and every gate. Already we have seen in the previous chapter logical operations like AND, OR, NOT. So exactly you know the working of AND, OR and NOT. Now what we are going to see here is what is AND gate, what is the symbol used, what is the truth table, and what is the output expression, and where exactly we can make use of these gates. So I am going to start with the first gate, that is the AND gate. So first we will be looking into the AND gate. So what is the symbol used basically for an AND gate? Now this is a two input AND gate. It means we have two inputs to this gate and one output. Let the first one be A, the second input be B. So what will be our output? For example, if I say F is equals to A dot B. So we use this symbol dot here. So it means A and B. This is the symbol what we use it for the AND gate. Now we'll see the truth table. Already I've seen the truth table in the previous chapter, but let us see that again. So since we have two inputs A and B, what are the different possible combinations you can have? How many? 4. So we have 0, 0, 0, 1, 1, 0, and the last one is 1 and 1. These are the 4 possible combinations. 0, 0. Now what we have learned in the AND operation is, for the output of the AND operation to be 1, the input need to be 1. All the inputs need to be 1. That is how the AND operation works. It means if the inputs are 0 and 0, the output will be 0. 0 and 1, the output will be 0. 1 and 0, the output will be 0. 1 and 1, the output will be 1. This is the truth table for the AND gate. You have seen the symbol used, you you're seeing the output expression, you're seeing the truth table. So this is a truth table for the AND gate. Now it is very important for us to understand what you mean by 0, what you mean by 1. It means you are going to give 0 volts here and 0 volts here, and when we test over here, the output has to be 0 volts. I'll give one more example here, 1 and 1. What does 1 and 1 means? You're giving here plus 5 volts, plus 5 volts. So when I test it over here, it should be plus 5 volts. That is how the AND gate works. That is what it means. 0, it means we can say 0 volts, and 1 indicates 5 volts. Is it fine? So we have just finished with the AND gate. So we have seen the symbol, expression, and we have seen the truth table. Now here we are talking about 2 inputs. We can have even an AND gate which has 3 inputs, A, B, C. So what will be your output here? F is equals to A dot B dot C. So this is a 3 input AND gate. We can go further with the 4 inputs and so on. If it is a 3 input, so what will be your truth table? The truth table will slightly change. Since you have 3 inputs, so it is A, B, C, and you have the output. In our case, we are given it as F. So it is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and the last one is 1, 1, 1. Now we are aware that all the inputs need to be 1 for the output to be 1. So I know that only in this combination the inputs are 1, 1, 1, my output will be 1. In all other cases, your output will be 0. This is 3 input AND gate. So we have seen 2 input AND gates where there are 2 input signals given and a corresponding output. Then we can see 3 inputs where 3 inputs are given and the corresponding output. So what is the output expression? The output expression will be F is equals to A dot B. Here F is equals to A dot B dot C. It means it is A and B and C. That is what it means. Now we will go to the next gate, that is OR gate. And I am not going to mention over there 3 inputs, we will restrict ourselves to 2 inputs. So now we will see the next basic gate, that is OR gate. So first we will look into the symbol of this, and 2 inputs are there, A, B, and this is the output. This is a symbol we use it for 2 input OR gate. Now already you have seen it in the Boolean algebra chapter that OR gate works in this way. One of the inputs to the OR gate or to the OR operation is 1, the output will be 1. that is what we have learned. So if I show you the truth table, A, B, and the output F, 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0, it means I'm going to give 0 volts here, 0 volts here. So what will be the output? 0. In the second case, I'm going to give 0 volts here, 1 volt here. It means the output what I get over here is 1, that is 5 volts. Similarly here also it is 1 and 1. So what is the output expression you have? F is equals to A plus B. So the plus sign indicates OR. It is A or B. So we have seen two gates now. One is AND gate, the second one is OR gate. We will be moving towards the third gate, that is NOT. So the third of the basic gate is NOT gate. Now the NOT gate has one single input and one single output, and this is the symbol we use for the NOT gate. Now NOT gate is also called as a inverter. This is a question normally we get it in final board exam. What is NOT gate also called as? Or we can get the reverse of this, which gate is called as an inverter. So this gate is called as an inverter because if I give here the input as A, the output will be A bar, that is complement. So if I give the input as 0, I should get the output as 1. If I give the input as 1, the output will be 0. So look at the truth table. If the input is 0, what should be the output? 1. If the input is 1, the output will be 0. So exactly the inverse of the input. That is what we can see here. So we have gone through three basic gates: AND, OR, NOT. All three gates are very important. So now we will be going into the derived gates. If you remember the derived gates, these are the gates that has been derived from the basic gates. So the first gate we will be looking into is NAND. Now, the symbol used for the NAND gate. So if A and B are the input, what will be your output? F is equals to A dot B the whole bar. This is a symbol, we use it, and this is the output expression we have. That is F is equals to A dot B the whole bar. Now I'll simplify this symbol further. If I simplify this symbol further, it should be this way: AND gate which is connected to a inverter. A AND gate which is connected to a inverter. So the output of the AND gate is given to the other gate, that is a NOT gate. Now if A and B are the two inputs, what you are going to get over here is A dot B. Now A dot B is given as an input to the NOT gate. So what will be the output of this gate? A dot B the whole bar. So when we simplify, it becomes more simple for us to understand that this NAND gate is broken into two parts. One is the AND gate, the second one is the NOT gate. So the output of the AND gate is given to the NOT gate, and this is what we get as the final output. So we come back to this. So the inputs are A and B. F is equals to A dot B the whole bar. Now we'll obtain the truth table, A, B and the output. 0, 0, 0, 1, 1, 0, 1, 1. So if I give the input as 0 and 0, what will happen? 0 dot 0. So we can take it in this way. I'll show it here. It is 0 dot 0. What is 0 dot 0? That is nothing but 0. So complement of 0, it becomes 1. Right? Is it fine? Yes. Now we'll go to the next one. What is the input of A? 0. What is the output? 1. Right? So it is 0 dot 1. So instead of 0 here, this becomes 1. What is 0 dot 1? 0 dot 1 is nothing but 0. So complement of 0, it becomes 1. So similarly here also it becomes 1. The last one is interesting. Let us see. Now here both the inputs are 1. It is 1 dot 1. So what will be your output? 1 complement. What is 1 complement? 0. So this is the truth table for a NAND gate. We have seen here the symbol, the output expression and the truth table. So what you can observe from this, if you have the truth table of AND gate, you can see that the output is exactly the reverse of the AND gate. For AND, when these two were 0, what was the output? 0. For AND, when these two inputs were 1, what was the output? 1. Here it is 0. So it is exactly the inverse. Why it is inverse? Because we are giving the output of the AND gate to a inverter. That is the reason the output is the inverse of the AND gate. Is it fine? Yes. Now we'll go to the next topic, next gate, that is a NOR gate. First we'll draw the symbol of the same. Again, I'm taking two inputs, A, B. So what will be our output? F is equals to A plus B the whole bar. Now if I simplify this further, in fact, I'm going to get OR gate. The output of the OR gate is connected to an inverter. Now for example, A and B are the two inputs. So we have A plus B, and the output will be A plus B the whole bar. So again what we have seen here is the output of the OR gate is given to a inverter. And what we have seen in the NOT gate, we have seen whatever input we are giving, the output will be the complement of that, the inverse of that. So you're giving A plus B to this NOT gate, so the output has to be A plus B the whole bar. So we'll see the truth table for the same. 0 and 0. I'll put down the expression over here, A plus B the whole bar. So the first two values, of A and B are 0. What is 0 plus 0? It is 0. 0 the whole bar is 1. Now 0 and 1. 0 and 1, what will be the output? The output has to be 1. What is 1 bar? It is 0. So the next one also will become 0. The last one again, it's interesting. So it is 1 plus 1. So it will be 1 bar, that is actually 0. So again, what you can see here is the truth table that we obtained for the NOR gate. We can see the output is the reverse of the OR gate. That is important. The output of the NAND gate is the reverse of the AND gate. Output of the NOR gate is actually reverse of your or inverse of your OR gate. So now we can go to the next topic or the next gate. That is XOR gate. That is exclusive OR gate. This is again a derived gate. So what is the symbol that we use it for this? This is the symbol, basically we use it, and this is again I am talking about two inputs A, B. So what will be your output? Output is equals to A XOR B. So this is A XOR B, or I can have the expression as F is equals to A B bar plus A bar B. So your expression is A B bar plus A bar B. Now we will obtain the truth table for the same. Yes, now I will put down the expression over here, so it will be closer to us. A B bar plus A bar B. So what is the value of A now? 0. So it is 0 dot 0 bar plus 0 bar dot 0. Now any one input to the AND gate is 1, the output will be, sorry, any one input to the AND gate is 0, the output will be 0. So it is all 0. So the output over here is 0. The next one is 0 and 1. So it is 0, this will be 1. Right? So it is 0 dot 1 bar. What is 1 bar? 0. So 0 dot 0 plus, what is 0 bar? It is 1 dot 1. Now what is 0 dot 0? 0 dot 0 will be 0 plus 1. What is 0 plus 1? Is 1. Similarly, here also we will get the output as 1. Now the last one, that is if both are 1. So it is 1 dot 1 bar plus 1 bar dot 1. So it is 1 dot 0 plus 0 dot 1. So the output will be 0. Now this is the truth table for 2 input XOR gate. Right? So we have seen the symbol used. We can even connect this, no problem. We can see the symbol here. We can see the output F is equals to A XOR B, or the expression can be F is equals to A B bar plus A bar B. That's the expression. And this is the truth table what we have got. The next one is exclusive NOR gate, that is XNOR gate, the last one. Again, this is a derived gate. So if A and B are the input, so how you write down? F is equals to A XNOR B, or we can write down the expression as A bar B bar plus AB. Now here, this is a new gate, that is XNOR, exclusive NOR gate, and you have two inputs. This is a symbol we used. The difference is there is a NOT you can see here, and this stands for XNOR, and the expression will be F is equals to A bar B bar plus AB. Now we will put these values and see how we can obtain the truth table for the same. So the two inputs, 0 and 0. So it will be 0 bar, 0 bar. So what is 0 bar? 1. What is B bar? 1. What is 1.1? 1.1 plus 0.0. So the output will be 1. 0 and 1, it will be 0. The next one is 1 and 1. So this will be 0, 0, and this will be 1.1. So what you get the output as 1. This is the truth table for XNOR gate. Now we also say that the XNOR gate is actually nothing but XOR gate connected to a inverter. So that is also the reality. So we have XNOR, that is exclusive NOR gate. This is a symbol. This is the output expression, A bar dot B bar plus A dot B, and the output is, truth table for the same is 0 0 1 0 1 0 1 0 0 1 1 1. With this we end with the basic gates and the derived gates. So once again I will talk about in short what is the AND gate. AND gate means the output will be 1 when all the inputs are 1. If any input to the AND gate is 0, the output becomes 0. The second gate we have come across is OR gate. What happens in the OR gate? The output becomes 1 when any one input is 1. Right? The third one was a NOT gate in the basic gates, and the NOT gate says what we input, the output will be inverse of the input. That means the complement of the input. Then we have come to the derived gates. Derived gates we have seen NAND gate, which we can say that the AND gate is connected to a inverter. Then we have seen NOR gate. It means OR gate is connected to a inverter. The next one we have seen is the XOR gate, right? And then followed with the XNOR gate. XNOR gate we can say XOR gate is connected to a inverter, right? So we have seen all the gates, basic as well as derived. Now we will see to the next one is which gates are called as a universal gates and why. Which gates are called as a universal gates? NAND and NOR, these two gates We call it as a universal gates. What is the reason? The reason is I can make use of a NAND to work like AND or NOT. Similarly, I can make use of NOR to work like AND or NOT. It means, for example, you are doing a practical and these 3 gates are not available and you need those 3 gates. What you have is a NAND gate, for example. Can I do my experiment? Yes, because I can make NAND gate to work like AND, I can make NAND gate to work like OR, I can make NAND gate to work like NOT. But obviously, we need some circuits for the same. So let us see, first is the NAND gate, how we can make use of NAND gate to work like AND or NOT. So the first one is for how I can make it to use like a NOT gate. NAND gate to work like a NOT gate. First, what is the symbol of the NAND gate? This is a symbol. Now, very important for me to realize is what is the truth table for the NAND gate. So, I am just going to write down the truth table. A, B, output 0, 0, 0, 1, 0, 1, 1, 0, 1, 1. So what we have seen in the NAND gate, when it was 0 and 0, what was the output for the same? It was 1. 1 and 1, what was the output? 0. 0 and 1, what was the output? 1. Now actually, we are looking at these 2 inputs. Now when both the inputs are 0, that means I am going to give 0 volts here. What will be the output? Output is 1. When I give both the inputs as 1, the output will be 0. So it means I need to short this. Now if I say this is A, it means I am going to give 2 inputs 0, 0. So what will be the output? 1, because it says that if both the inputs are 0, the output is 1. In my second case, if this is 1, A is 1, so what will be the input over here? 1. What will be the input to this input over here is 1. So it means 1 and 1, what should be the output? 0. Now if you look at the NOT gate, what is the working of the NOT gate? If you give the input as 1, the output will be 0. If you give the input as 0, the output will be 1. So that is actually the working of a NOT gate. So with this particular circuit, I can make the NAND gate to work like a NOT gate. Is it fine? So if I give this as A, what will be my output? My output will be A bar. So do I need a NOT gate now? No, because I have a NAND gate. By connecting this, I can make it to work like a NOT gate. Now we will see how I can make it to work like a AND gate. Right? Now look at the circuit. So you have A, B. So what will be the output of this NAND gate? A dot B the whole bar, right? Now if I give this to another NAND gate, but this is a NOT, right? So if I give this to this particular gate, the output will be A dot B, right? So I'm making this circuit to work like a AND gate. What is A dot B? The output of a AND gate. So with this we can understand, if I do some modification, if I do some changes, then I can make NAND gate to work like a AND gate. So even if I don't have a AND gate, I can still work with the NAND gate, right? So what we have seen here is how we can make NAND gate to work like a AND gate. Now next we'll see how it can be made to work like a OR gate. Now this is a circuit where I can make this circuit to work like a OR gate. Let us see. So you have A, so the output will be A bar, B bar. So this will be A bar dot B bar, the whole bar. Now this is nothing but actually A plus B. Now how we get actually this is by applying the De Morgan's theorem. So De Morgan's theorem is so important. What you have learned in the De Morgan's theorem is A plus B the whole bar is equals to A bar dot B bar. A dot B the whole bar is equals to A bar plus B bar. This is what we have done. So by applying it, we can actually get A plus B. A plus B is nothing but, so I can finally write down here it as F is equals to A plus B. So A plus B is nothing but the output of a OR gate. So by drawing this, we can make this circuit to work like a OR gate. So we have seen NAND gate can be made to work like a NOT gate, AND gate and the OR gate. So the next we'll see is how we can make a NOR gate. How we can make a NOR gate to work like a AND, OR and NOT. Right? So for that, it is very important for us to look at the truth table. What is the truth table? First, I will show you the symbol A, B. So this is A plus B the whole bar. So 0, 0, what will be the output? Output will be 1, 0, 1, 0, 1, 0, 0, 1, 1, 0. Again, what is interesting for us is this 2 initially when we talk about the NOT gate. So when the inputs are 0, what is the output? 1. When the input is 1, the output is 0. So it means it works like a NOT gate. So I can make this NOR gate to work like a NOT gate. Let us see. So if I am going to give the input as A and initially the values are 0, 0. So what will be the output of this? The output will be 1. If I give the value of A as 1, then the output will be 0. So you can see here with the NOR gate, if I short this gate will work exactly like a NOT gate. So the next one is how I can make this to work like a OR gate. So this is A, B. So what will be the output of this? A plus B the whole bar. A plus B the whole bar. Now I'm going to make this work like a OR gate, right? So if this is A plus B the whole bar, you're giving it to an inverter, NOT gate. So NOT gate means the complement. So what will be the output for the same? The output will be A plus B. A plus B is nothing but the output of a OR gate. So by this diagram, by this circuit, I can make a NOR gate only by using a NOR gate to work like a OR gate. The next one we'll see is how we can make it to work like a AND gate. This is A for example, this is B. So here we are going to get A bar because this is a NOT gate. This is again a NOT gate. This becomes B bar. We are giving A bar, B bar to the NOR gate. So the output has to be A bar plus B bar the whole bar. Now by again applying De Morgan's theorem, I have given here the De Morgan's theorem. You can see here, by applying De Morgan's theorem, I get the output as A dot B when I convert this. A dot B is nothing but the output of a AND gate. So we can see here, this circuit, I can make a NOR gate to work like a AND gate. So what I have done here is, I have shown you why NAND gate as well as a NOR gate is called as a universal gate. And I shown you with the circuit that these gates can be made to work like a AND or NOT. That is important. So we have understood what is a universal gate, which gates are called as a universal gates, right? Now we'll see one small circuit. Now if I tell you, draw the circuit for the same. Now this is a sum of products. So you have plus sign. This is actually, you can say C dot D and A dot B. So you can see here sum of the products. So what I'm doing here is I'm saying OR. It has how many inputs? We say 1, this is 2. So I have 2 inputs, right? Now this one input, we get it from where? From the AND gate. So, and the input to this AND gate is A and B. This is the AND gate, second AND gate, and we get it from where? From C and D. So, C and D. So what will be the output of this? This is A dot B. This is output will be C dot D. This we are giving it to a OR gate. So this becomes A dot B plus C dot D. So this is a circuit which we have drawn. Now I would like to give you a simple example. What we basically do here is, in the Boolean algebra, we try to reduce the expression by using the algebraic method or maybe by using the K map and so on. I'll give a fine example. for example, I have an expression AB plus C D bar plus C D. Now for example, this is the expression I have and I am told to draw the circuit. So what should I do? This is the sum of the products. So I can have 3 inputs. The first one is A, CD, CD bar. So this is A, B, this is C, this is D, this is C, this is D. So this is the circuit what we will have. So this is the output. This is the output what we are going to get. So you can see here I am using 3 gates, 1 inverter and 1 OR gate. Now for example, I reduce this expression. If I reduce this expression, I may get this expression as AB plus we can keep C as common. So I'll get D bar plus D. What is D bar plus D? Is 1. So AB plus C. So this expression I have reduced it to AB plus C. Now we'll look at the design part. So how the design part will be, say, there are 2 inputs, fine. One is C, the other one is AB. Right? Now, can you see these 2 circuits? Can you see how many gates have been reduced? Yes. So, Boolean algebra plays a very important role. So that's the reason we have actually learned the previous chapter so that the size of my circuit can be reduced. This is a very small example I have given where you can understand why actually I need to do this. So this is what I have done on the circuit for this expression. When I reduce the expression, I get this, and this is the final circuit when it is reduced. So you can see the number of gates that has been reduced over there, right? With this, I end my session. Thank you.